So thank you, Johan, for the kind introduction, and thank you, everybody, for turning up this morning, particularly after the festivities you all enjoyed last night. It's always interesting to open the second day of a conference, because on the one hand, you get to build on everything that went before, but on the other hand, you have to follow up, and you have to kind of follow what went before, and yesterday's speeches were set a very high bar. So my name is Niall. I'm here to talk a little bit about greenhouse gas removal and the 1.5 degree target, and I obviously have to recognize and thank my sponsors, particularly Total and IEA GHG, since they're here in the room, but also the TCCS Research Centre, NERC, and EPSRC, who've really helped fund the work that I'm going to present to you here today. So Paris changed everything, right? Before we were speaking about more or less mitigating and climate stabilization and so on. And then at a certain point, we started speaking about targets like 2 degrees. And then in 2015, we got on to speaking about efforts towards this 1.5 degree target. And so this means that in addition to the conventional attempts to decrease and mitigate CO2 and other greenhouse gas emissions via carbon capture and storage, renewable energy, and so on, we also now need to go beyond net zero into potentially a net negative world where we're pulling large amounts of CO2 out of the atmosphere. And it's worth pausing, I think, when we look at these figures, to look at the scales on the y-axis and to recognize that by the end of the century, the amount of CO2 that we're potentially needing to pull out of the atmosphere is not that dissimilar to the amount of CO2 that we're currently putting into the atmosphere. So this is a really significant challenge. There are many paths, according to the IPCC, to get us to this 1.5 degree target. Depending on which pathway you choose, you could do this with effectively reducing energy demand, a little bit of energy efficiency, some renewable energy, and in particular, land use mechanisms. Many of the other pathways require other more engineered solutions, and in particular, this bioenergy with carbon capture and storage piece. However, when we're evaluating the feasibility and likelihood of these different scenarios, it's always worth thinking about what the world is currently doing. And yes, there's a strong suggestion that we're going to do a lot more with renewable energy over the course of the next couple of decades. But there's an equally strong suggestion that fossil fuels for power and transport and heat will continue to provide a very significant part of how we get our energy going forward. If you look at, for example, China, India, Southeast Asia, and so on, the amount of coal and natural gas that they're going to deploy over the next couple of decades is in combination very significantly greater than the existing US fleet. So on that basis, I would sort of suggest that these sort of scenarios that propose that we do not need technologies like greenhouse gas removal, BECCS, and so on, they're unicorn scenarios. They're infeasible, and I would go as far as to say they're actually quite unhelpful because they're not facing up to the reality that we actually are, stuck with. So to that end, I'd suggest that carbon capture and storage, CCS, and greenhouse gas removal, GGR, they are integral to the 1.5 degree target. And in that context, and for now, I'm going to speak primarily about bioenergy with CCS, BECCS, because it's the option that makes its way into most of the modeling scenarios. Of course, there's an entire portfolio, and we'll get to that later. But speaking specifically on BECCS, so there are a couple of key questions. It is a persistently controversial technology, so I think it's fair to ask the question, does it actually work? Does it do what it says in the tin? Does it remove CO2 from the atmosphere? There's another question around, what does it actually do? What's its purpose as we integrate it into our economy? Is it a technology that primarily pulls CO2 from the atmosphere and along the way generates a little bit of power? Or is it a technology that converts biomass into bioelectricity and, by the way, removes some CO2 from the atmosphere? What's its primary purpose? Because this will really inform how it's incentivized, how it's remunerated, and how it operates. There's also then a question around who has to do what. So by that I mean, we have global targets, but how do you then allocate responsibility amongst regions and equitably amongst countries, recognizing that the historical responsibility for the current climate crisis, as it's called, goes back well over a century. And then the final question that I'd ask is, can we go it alone? Can individual countries take on this burden by themselves? Or is there a very real and important need for international cooperation? I think you can see where my bias lies with that one. The lens that I use, or that myself and my research team use to look at these problems, it's called the Monet framework. Monet stands for Modeling and Optimization of Negative Emissions Technology. So the idea is that this tool can incorporate BECCS, afforestation, enhanced weathering, direct air capture, and so on. Obviously, models like this need quite a lot of data, so crop yields, crop residues, the availability of different types of land cover, how much CO2 storage we have available. And that last one is really important because, broadly speaking, we don't know enough about what CO2 storage is where. Obviously, things change with time. So as we go across the century, we have our different CO2 removal targets, and then we have different rates of change as how the world is expected to tend to decarbonize. We break the world up into a number of what we think are particularly important regions. Contiguous United States, EU 28, still includes the United Kingdom, Brazil, India, and China. So this gives us, I think, a pretty good spread of east-west and north-south climates and countries, but also a good spread of economies. So we're not trying to give you a very detailed and absolutely correct answer, but rather an impression. So again, the name Monet is sort of quite fitting, I think. So to answer the first question, or to at least address it, the question of does it work? Does BECCS, in a scalable and timely way, remove CO2 from the atmosphere? And the answer is very, very much, it depends. So on the y-axis here, you're looking at the cumulative CO2 removal from the atmosphere as you start a project at T0 and go forward. Depending on the choices you make at the beginning, so I think this scenario is a miscanthus feedstock planted in Brazil and then moving that biomass to the UK. Depending on the choices that you make, so for example, the red line would correspond to doing something like chopping down the rainforest in order to plant the biomass, and on the blue curve would look more like using marginal land. You incur a greater or lesser carbon debt to begin with. Then all of the choices you make along that supply chain, as you cultivate, harvest, process, transport, and finally combust and store that carbon, all of those choices dictate the rate and scale at which you can remove CO2 from the atmosphere. And I think most of us would agree, ladies and gentlemen, that a BECCS project that took approximately 3 decades to actually start removing CO2 from the atmosphere probably wouldn't be very much help at all. So I think all of these things need to be carefully monitored and evaluated as these projects are being prosecuted. Similarly, does it generate power or does it remove CO2 from the atmosphere? So here we're looking at a net energy balance across, again, the entire supply chain, articulated in units of electricity, so it's an electrical energy equivalent. The x-axis is the amount of capacity that you would need to meet a given target. So I think this target was 50 megatons a year, so something like what the UK might need to do. The size of the symbols corresponds to the amount of land area that you would need. Small symbol, small land area, big symbol, big area. And then the color corresponds to the water use. Blue, not much water. Yellow, really quite a lot of water. And again, you see that all of the choices, so for example, if you're taking willow, cultivated in Louisiana and brought to the UK and converted in a relatively inefficient power station, you need quite a lot of land, quite a lot of water, and you actually are you're a drain on the world's energy system. You're not helping out. Conversely, you could take, using agricultural residue and things like that in the UK, and you could do quite a lot better in terms of your energy balance, water use, and so on. What you also see is that there are sort of 2 tranches, or 2 sort of sets of types of projects. One where you're using quite inefficient power stations to meet this carbon removal target, and then another where you're using a much more efficient system to meet that target. What you see is that the more efficient systems are obviously better at producing electricity, but you also need quite a bit more capacity. In other words, you need to build more stuff. And in other words, it'll also likely cost you more money. So again, what are you trying to do with this technology? Are you trying to remove CO2 from the atmosphere, or are you trying to generate biorenewable electricity? As we integrate these technologies into our electricity systems, and we're moving from a trajectory towards a low-carbon energy system to a carbon-negative energy system, we observe some really interesting structural changes. What you're seeing here on the y-axis is the electricity or the energy supply for a UK-type system. It is the UK, going back to about this time last century. And you see how we've had a predominantly thermal power supply up until sort of the beginning of this century. And then as we've embarked on this transition to a low-carbon energy system, the amount of renewable energy we've decided to use really increases. But in the second half of the century, as we then need to go net negative, there's this resurgence in the amount of thermal power that we need, because whilst wind and solar power are absolutely fantastic, what they cannot do is remove CO2 from the atmosphere. So there is an important qualitative and structural impact on our energy systems as we go net negative. And whether this is BECCS or whether this is direct air capture, this impact remains. As with the energy trilemma, there's also a carbon-water energy nexus, or another NETS trilemma, where we're trading off the technical performance, the resource efficiency, and also the economic and environmental impacts of these technologies. So just to look at this quickly, you're looking at the water use as we meet different UK carbon removal targets, depending on whether we're meeting these targets, minimizing water use or minimizing land use, maximizing the CO2 efficiency across that supply chain, or maximizing the energy produced from that supply chain. And you can see that as you move along these objective functions, the amount of water that we need really increases. You can do the same exercise for land use. And again, the point being that if we myopically focus on just carbon dioxide removal or energy production, we could bring ourselves into very unsustainable places in other parts of the ecosystem. Going back to this question of who has to do what, so we know that there are kind of global targets, but then how much you share this out. And there are many different approaches for burden sharing. And the key, I don't want to go into this in detail, but the key point is that depending on how you share this burden, different countries could find themselves being asked to do quite a lot. So for example, if we just thought about on a population basis, you'd see countries like India and China needing to do really quite a lot. Whereas if we thought about historical greenhouse gas emissions going back to pretty much the beginning of the Industrial Revolution, you would see countries like the United States needing to do an awful lot more. So you can imagine quite quickly that this is going to be a persistently controversial topic in international negotiations. As you zoom then into sort of within regions, so for example, looking at how the EU might need to meet its targets, again, looking at responsibility versus capacity, i.e. GDP, or needs, so that's a population basis. Again, the amount of responsibility, how that burden might be shared out, would vary dramatically. So for example, on a capacity basis, we could see that Ireland needing to do more greenhouse gas removal than the United Kingdom. But on a population basis, not so much. So this again will be something that we'll need to tackle very carefully. This is important because not all countries are equally endowed with the indigenous capacity to remove CO2. So again, thinking about this through a BECCS lens, you can see, for example, how different countries have different biomass potential and also different storage potential. So this obviously ignores contemporary political concerns. So if you think about Germany, has a relatively abundant supply of carbon storage, whereas Spain, for example, has an abundant supply of biomass. In all cases, the red lines correspond to sort of the limiting potential. What's worth noting, though, is you can see from the symbols, these are the different quotas that will be assigned. Countries like Spain or Germany will have no problem meeting any of those quotas. Countries like Austria, however, can't meet any of their quotas acting alone. So this then tells us that having countries work together to exploit and best use their existing natural resources will be key to delivering these targets in a socially equitable, technically feasible, and economically viable way. Coming back up to a more global picture, again, we see the value of cooperation. On the x-axis, you've got the total CO2 being removed, and the y-axis, total cost. Surprise, surprise, if we cooperate, we can remove the most CO2 for the least cost. If we don't cooperate, our ability to remove CO2 from the atmosphere is reduced and the cost goes up. What's interesting is that we sort of see different types of countries, and I really need to emphasize the fact that these countries are not, this is not meant to be, this is the answer for India, but it's an archetypal country. So for us, in our model, India is a country, and Brazil also are countries that have the potential to produce quite a lot of biomass, but they don't have an awful lot of well-characterized storage. So regions like China, their exclusion, the rest of the world can still meet their targets, albeit at a rather large cost. But excluding countries like India and Brazil, if they can't cooperate, the amount of CO2 that we can remove tends to get reduced. Cooperation, it would appear, will be vital as we move forward. So thanks, Doug, if you can go. So this is just a sort of a video of how BECCS might get deployed under a P2 type pathway going forward. So this is P2. We don't need to do that much. We can use relatively small regions as we start out in China, little bits around Europe, quite a bit in the United States. So this is sort of a relatively easy lift. We can do pretty much all of this with marginal land, and we focus on areas that have good storage and relatively low cost. If we go on to P3, you then see where we've got a lot more work to do for removing CO2 from the atmosphere. Again, we start off in China, but now the whole world has to come in. What's really important about these larger targets is that they cannot be met using only energy crops on marginal land. We have to start encroaching on other types of land. This may not be sustainable, and so we need to think about how we might tackle that. The obvious answer is probably don't try and do it all with just BECCS. Again, this is what the cost supply curve looks like for P2 along the top, and then P3 in the bottom. I guess a key point would be that, as you start out, you use the cheapest and easiest options, but after a certain point, you do see this sort of spike in prices, consistent with what we see coming out of the IAMs, but also at these prices, I think even the most skeptical people would say, okay, maybe we might want to look at some alternative technologies like direct air capture, which is fantastic, and it may indeed have a role to play. But it's again important to note that direct air capture will integrate with the existing energy system. It will require quite a lot of energy, and so therefore, in order for direct air capture to remove CO2 from the atmosphere, it will need to have a scalable source of low carbon or ideally zero carbon energy, so heat and power, to run that system. And looking where the world is today and this is a low temperature solid sorbent type system, the energy systems of India and China, some parts of the United States and some parts of Europe, will be unsuitable to run a direct air capture facility. I'm just conscious of time, so I'm not going to go through this slide in any real detail, but the key point that I want to make is there is indeed a portfolio of options for removing CO2 from the atmosphere, and each of them have their independent challenges. In the context of CCS, we've often spoken about the importance of secure long-term storage for CO2. Direct air capture and bioenergy with CCS, where you geologically sequester that CO2, that in my view corresponds to a permanent and secure form of storage. Some of the land use options, much less so, and understanding how to cost and price that risk as we move forward will become very important. So, to conclude, some tentative or thoughts at this point. So does BECCS actually work? Maybe. It really relies on making astute decisions along the supply chain, and we need to really think about the entire kind of ecosystem impact of going down that road. What does it do? Well, so as we incorporate this at scale into our energy system, there will be significant impacts. Carbon negative is fundamentally not the same as low carbon. I think international cooperation is going to be vital in meeting this, in meeting global targets. Sorry for the typo. Mitigation, I think, so going from high carbon or carbon emitting to low carbon or zero carbon, that's something that broadly speaking countries can take as a sovereign decision. They can do it by themselves and they can decide how to get there. I don't think that's the case as we go to something like greenhouse gas removal. I think that's an inherently international challenge, and consequently a portfolio of GGR technologies will be required. Thank you all very much for your kind attention.
Thanks a lot, Niall. We have time for one or two questions, and thank you very much for giving us this very broad and comprehensive overview of BECCS and what these negative emissions can be. So that was very helpful, I think. Many people wonder about this, I guess. So, Niels Røkke.
Thank you for an excellent speech. I was wondering, this paper you're referencing, was that part of the IPCC report background? Because it seems like it's kind of suggesting that the special report on 1.5 degree is simplified and doesn't take all these factors into account, because they're talking about 900 mega hectares or something you need to offset the emissions in the P4 scenario. And you're looking to, you know, if you just look at what you need and don't look at the whole chain, this is not going to be feasible.
So you're talking about the papers that went into sort of land use, water use associated with?
Yeah, the 2017 paper.
Yeah, I'm not sure. This is the short answer. I don't know if it was referenced in the...
But are they wrong and you're right, or...?
No comment.
Simple answer, you know, I'm always right, you should say. Okay, one more question? Okay, Niall, thank you very much.
Thank you.